Hello everyone, my name is Maz Barami from Wolfram Research. Today we will see the ninth session of live coding with Andreas Lauschke. Andreas is a senior mathematical researcher who has been using Wolfram technologies for over 26 years. Today he will dig deeper into the date, time, and calendar functionality that we have readily in the kernel. These functions are extremely important for any data scientist, as a lot of data he needs to work with is time-stamped, from annual data like macroeconomic numbers down to the second by second or even sub-second time-stamped data like financial trading data. Handing over to you, Andreas. Looking forward to your next session.
Great. Thank you very much, Mats, for the introduction. Hello, everybody. Welcome to my session number 9. Today, I'm talking about the date, time, and calendar functionality that we have in the Mathematica system. It got a major overhaul, I believe, in version 9 and is now ready at our fingertips with very, very much advanced functionality that makes a lot of queries and computations very easy. And as Matt's already said, that is very important to handle for the data scientist, because a lot of data is simply time series data or event series data. So we have it in financial data, we have it in a lot of areas. A lot of the data that we're analyzing is timestamped or time series data. So let's jump right in it. So let's first begin with the definition of what is time even, what is time itself. Time is the indefinite monodimensional physical quantity that expresses past, present, and future progress and events. So that can be dates, for example, June 17, 1953. It can be an instant in time. So for example, this list would specify exactly to a sub-second level one particular instant in time. And it can be durations like 3 minutes, 5 days, 7 weeks, 27 years. And what we have in the kernel is we call it a data object. And this data object makes many things incredibly easy. So let me give you an object-oriented analogy. The date object can be used both as a constructor and as a container. So if you have a background in object-oriented languages, Java, C#, whatever, right? Or more modern languages like F# or Scala, you're familiar with objects. So let me show you date object as a constructor. When we just say the date object, then we get this particular instant in time that we're having right now. So at the Eastern time zone, it's 17:03 and 18 seconds when I just evaluated this on Friday, the 4th of October. And what this really does internally is that it creates the date object using now. And now is the expression that you would submit in order to get this current timestamp, this particular spot in time, this particular instant that we have at the very moment that you submit it. So this is what's really going on if you just query for the date object itself. And we can give date object many different input formats. For example, we can give it a string in a particular string specification. We can give it a list that consists of year, month, day, and then come hour, minutes, and seconds with sub-seconds. Or we can also give it a number, just an integer. In that case, it's using absolute time, and I'm going to cover absolute time in a moment. So when I submit this, then I get these date objects that you see here, and I've created them by using different types of input types, right? String, list, or absolute number. Okay, so we can now further query it, right? We can take a date object that exists and ask for the day. So when we give this full date object specification and ask for the day, we get this one particular day. And it's formatted as a date object at the front end, but we can also look at it in the full form. And here we see it's a date object consisting of a list for the date part. I asked for the day here, that was my query. It's a Gregorian calendar. And here I gave a GMT -5, so this is Central Time. Okay, and we can query now for different types. We can type for the minute, we can query for the day, so this would be the day here, for the week, for the month, for the year, the decade, for the millennium. And this simply allows you in the second argument to specify what in the date object you're looking at. And there are other ways to create time instance, but then they are not necessarily date objects. So you don't necessarily need a date object in order to manage time. So, for example, absolute time is the number of seconds, I believe, since, I forgot, I believe the January 1st of 1900. And we can now query with absolute time and look at these integers. These are large integers. Yes, it is the 1st of January, right? That's why I put these two here. So this is now the number of seconds since January 1st, 1900. When I specifically asked for the first day, here we get 0. So a year later, we would have this number of seconds, and a day earlier, we would have this number of seconds, and so forth. And the difference between them in a year would be this number of seconds. And the system is smart enough to consider leap years. That's also something we're going to look at in a moment. And we can use different input formats, right? We can use the string, day name, month, then comes a slash, then comes the year short name. And that would be the third one, I think this one, and so forth, right? This is a typical format that is used in America, and you can specify this as a string concatenation of these elements that you need. So for example, the last one would be Friday, 26 December 1980 at 0000, right? We didn't give it any time, so this becomes all zeros here. Okay, for more info, see the help browser on DateString. It's a very flexible function. You can define your own date formats. You can use predefined format strings. It's very, very powerful. And have a look at it. It's more than I can possibly present in a session. But date object can also be a container. For example, I can provide a date object, and then I can look up properties. So these are things that I can now look up with properties. And we can now use the date objects for many different things. For example, we can look up the time zone. And in this one, we have CDT, so that comes to America, Chicago. The time zone is one of the properties that we can query here. And there are several different other ones, of course, minute, hour, day, week, month, year, and so forth. And in this notation, we are now getting back quantities. You see that this is kind of light brownish shaded. So at this particular point, we have 0 minutes, 13 hours, 18 days. That's all specified here in this date object. When you look at 13:00 and 01, you have 0 minutes, you have 13 hours, right? That was provided here, and so forth, right? 42 weeks, 10 months, 218 is the year. So these are these properties that you can look up here at this point. And if we do this with right now, right, you see that it's 9 minutes past the hour. It's 5 p.m. in my time zone. It's the 4th day of the month, the 40th week, the 10th month, and year is 2019. Keep in mind, these are now quantities. And we have also a lot of functions that allow us to make more advanced leap year calculations. And with the capital Q, when the function ends, with the capital Q, it's a Boolean, right? So you should get a true false. So as of right now, and we are in a leap year? No, 2019 is not one. And the 5th of May in 2020, is that in a leap year? Yes, right? We're getting back the true. I have to give you a little bit of a nerdy excursion. The kernel uses the proleptic Gregorian calendar for dates before the Gregorian was officially introduced in 1582. Have a look at this particular wiki page. I can't really go into it too detailed. To explain it a bit better, I've written you a footnote here. Have a look at that when you download the notebook. It explains why for the Gregorian calendar there is no year zero. So we're going from 81 to 1 BC. And this means the following would be an improper usage to find the pre-Gregorian leap years, right? We are trying to go in steps of 100 because we know that every year divisible by 100 is not a leap year. But if it's divisible by 400, then it is one. So if we're looking at all these ones here, we would expect a leap year at minus 800. They're all false here, right? Before year one, everything comes back as false if they're divisible by 400 or not. All these multiples of 100 are false. But after the year one, they suddenly divisible by 100, it's false. Divisible by 400 is true. So 400 is true, 800 is true, and 1200 is true. All right. So there's a jump in this. There's an inconsistency, but that's because we have to use the proleptic Gregorian calendar. The correct way to query for leap years is that we are now on this multiple of 4, but on off years, right? So if we go to 1, then we would see that here. So the year before 0 was a leap year, and the year 0 was a leap year. And then we're going forward in multiples of 4. And when we are in multiples of 400, we are leap years. And otherwise, when we're going in multiples of 100, we are not. You see that the year 300 is missing. But that's after the year 1. Before the year 1, we are on a different scale. Suddenly, the leap years are actually odd. They're all odd numbers at this point. Okay, so as the data object is both a constructor and a container, it's entirely possible for an expression to appear with the head of data object, but not represent a valid date. And in such cases, data object Q can be used to test the validity. So, for example, I can ask data object Q of no. Well, yes, that's true, because as we've seen earlier, no gives us a data object. But if I just say something that's foo and notice that this is blue, so it's not evaluated yet, how can this possibly be true? So it's false. And if we're asking for this particular data object, it's false. When we have to look at this, Wednesday, October 14th comes back as a false. And now I want to show you the most, perhaps the most important thing to understand about the data object. It currently, in the current version of the Mathematica system, it contains 4 principal elements that constitute a date in the language. So there's a date part. That's the data that specifies what particular date you're looking at. That's how you specify it with a date part. We need a granularity. In this case, it says instance, so it's a point in time. Then we need to specify a calendar type. Here we say Gregorian, and we need to specify a time zone. In this case, -5, that's Central Time. And all of these elements are necessary to fully resolve a date to a given moment in time. So now let me talk about the data object representation. The first argument is the representational expression of the date associated with the calendar. Right? This is typically a list of 1 or more elements here, this first part that I've showed you. But in principle, it can take several other forms. And the representation is fundamentally tied to the calendar associated with the date. So if you change the calendar type to something else, a Jewish calendar or Islamic calendar, you will get different results. So the first of the data object is this list, right? This is this list that we're having right now. It's 5:15 in the Eastern time zone right now. Okay, we also have date list. That is another representation, and very often we will find this much more suitable. And you see different formats for the date part when you use a different calendar. For example, if for the calendar type I say absolute time, then we can get a totally different representation. I'm saying 0 here at this moment. So that's for the date object and the date list. We're probably going to use the date list more frequently now. And as date representations, we can have date list, absolute time, date string, Julian date, Unix time, and CD real time. I don't know how to pronounce that. And we get different results depending on how we query this. Right? The date list we see here, that is pretty much similar to the date object. The absolute time is the number of seconds since January 1st, 1900. A date string now contains a string containing the different date string elements. Julian date uses the Julian calendar. There's also Unix time and this unpronounceable date type. So the next part is the granularity, right? Remember the second part here is the granularity, where here we're saying instant, but doesn't have to be. So the granularity represents a calendar object, including and beyond a single instant in time. We have a flexible framework for this, and so that's why we can say year, month, or date, right? Or second, or minute, or week. Granularity is fundamentally tied to the calendar associated with the date and can be either canonical, such as a year, or derived, such as a quarter. So let's look at part 2, and that says instant, right? And we look at the full form, we see that this date object now represents an instant. The second element is instant, as we've seen. And in the full form, we see that again, when I say today, well, then it's not an instant in time, it's a time span. So now we see the full form contains day in the second position. And here is a list of the currently supported granularities. If you want to look at them, again, I'm using now here this particular instant in time, but here now are the granularities that are available. Instant is what we use for something like now, this particular point in time, and when we can query all of them, right? Which millennium are we currently in? This is the millennium. Which century, which decade, which year, which quarter, which week, and so forth, right? A plethora of choices that we have available to query. There are additional convenience constructors that we have. So we can, for example, say the current date. That refers to today. It wouldn't strictly be necessary. We could do it with a date object, but using current date or next date just makes things much easier. So, for example, the current day, week, month, week, we see all of them here that we have in this list. We can ask for next, and then in next we see the next day is Saturday the 5th. The next week is this. The next month, I'm sorry, I misspoke, month and week. The next year is 2020, and so forth. So these offset functions also accept a reference date for the offset to use. So for example, I can ask, what was the previous week of Wednesday, the 3rd of April, 2013? Well, here it is, right? So this gives you a possibility to create offsets. Okay, let's do a few more with next date and previous date. So when we evaluate this, then we're getting the next dates and the previous dates as we specify in this list. And we can also look up particular days of the week. For example, here I say Friday, and notice that the days of the week in the Mathematica system are not strings. You can specify the days of the week without providing the double quotes. So that's for next date, and that is for previous date. There's one problem that you should be aware of. I found out that next day and previous date are missing leap seconds. So for example, the last second of the year 2017 was actually 2016, 12, 31, 23, 59, 60. but that is something the Mathematica system does not have. The last second it has for 2016 is 23:59:59. So there's, in theory, there is 1 second missing because 2016 had a leap second. Okay, we can construct them in various other forms. We can ask for yesterday, we can ask for tomorrow, we can ask for the local time, and that gives us the correct time zone. We can also convert. So for example, when we ask for date list and give it the date as a string, we're getting it as a list in the typical date format. We have date string when we are including the seconds, the minutes and seconds and hours. Okay, then we get it as a date string in this format. What's the absolute time? And what's the absolute time of a date string? And this can sometimes be easier to read, right? It's a big integer, 3.7 billion, and that can be easier to understand than this fixed point number with 10 to the minus 9. We have functions to compare date objects. We can, for example, ask if today happened before tomorrow. But yes, is now the same as today? No, because now is a timestamp. Today is a period length. So that's why this cannot be compared, and we're getting the input back. Date object double equals date object. And we saw that earlier. Now is an instant, today is a day. There's also questions for containment. We have date within Q and date overlaps Q. We can use them to check for full or partial containment. So for example, is now inside of today? Yes, right? Every instant is part of the surrounding date. We can ask if the current date, the week of the current date, I'm sorry, the other way around. If the next Sunday is part of the current week. Yes, that's the case. We can ask if the next Monday is part of the current week. No, that's not the case, because Monday is part of the next week. We can ask, all right, is the week beginning the 29th of October part of the current week? No. And we also have date overlaps Q, not just date within, we also have date overlaps Q. So we can ask, does the week beginning Monday, the 29th October, overlap with the October? Yes, that's the case. But can today and tomorrow overlap? No. All right. So next, let me show you calendar types. And these are the calendars that are currently available in the Mathematica system. A Gregorian, Jewish, Islamic, Iso-week, Julian, Absolute, Unix. We have all these calendars available, and this column shows you where we are currently in different calendars. Okay, so let me skip that. We need time zone. And the time zones represent a region on Earth that observe a uniform synchronized time. We have 4 different input types for the time zone. There's numeric offset, time zone ID, location identity, and none. So numeric offset from GMT would be a real or integer or rational value. That's the number of hours offset from GMT. And there are currently 38 official numeric time zones that we have. Okay, so for example, let's take the moment right now and display it in -5, right? So let's display it in 6.78. This can be a real number. It doesn't have to be an integer. So this is a great way to specify what a particular time, date or time is in a different time zone. And the kernel originally initializes its local time zone using information from the operating system. And the dollar time zone is used as the default time zone value when not otherwise specified. So it's -4 because I'm in the Eastern time zone. We can use time zone ID and location entity, and sometimes also called the internet time zone. And we have currently 471 recognized time zone identifiers, which correspond to different geographic regions. So for example, if I query for Chicago in America, we're getting this return, which tells us it's in the central time zone. We can also use Timezone Entity, and again, I'm in the Eastern time zone. It's a long list, 471, so I'm using short in the output. And these are the Timezone entities that we have, right? Whatever is displayed, plus 397 of them. And the length is 471. Okay, so an entity with a position property may be used as a time zone specification when the underlying time zonality can be fetched from the Wolfram knowledge base. So for example, Bismarck in North Dakota is included. So here I get a valid return. And here we display it as a local time zone, and it's the same time zone as Chicago is in America. We can also use none. If we use time zone goes to none, then it doesn't immediately instantiate a time zone value in the data object, but instead it defers the determination of the time zone up to the point where it's required to resolve the date. So if I say data object now, time zone goes to none, you see that there is no time zone information. There's automatic. And with automatic, we can specify that we want an indication that the time zone should automatically be inherited from its argument and otherwise default to time zone. So let's do automatic. Again, in the display, we see GMT -4 because I'm in Eastern time zone, but it is still instantiated when we are inheriting from the argument. Okay, now come date-based computations. We want to add days, we want to multiply would be funny. We want to subtract days, we want to count them, and we want to use day ranges and so forth. So keep in mind, when it's just raw integers, it means days. So for example, let's take Sunday, 1st of January, 2017, and that's 35 days. Well, that's Sunday, the 5th of February, 2017. We can use the string date format for that. Again, getting Sunday, 5th of February. We can also subtract. So this is 35 days before that. We get Sunday, 27th of November, 2016. What do we get when we add 35 days to today? Well, it's Thursday, the 7th of November. And for other things, when it's not days, you need quantities. You cannot use integers there. So for example, take this date and you add 14 weeks. Okay, that's Sunday, 9th of April, 2017. Let's add 10 months. And again, this is light brownish, so that tells you that it's a quantity. This is unit months. When you look at the hover, there's a light blue background. It says unit : months. All right, let's add 40 weeks. Let's add 7 weeks and 2 days. Now you need a list of 2 elements here. Let's add 342 hours. Let's add 1 month and 15 days. Let's add 2.45 days. Let's subtract 4.6 hours. Okay? So we can use date plus, and for the next, well, I want to store that away in a variable that I call future. So let's add 19 business days. So take today and add 19 business days. So part of this is automatically a calendar, and the system knows I'm in the Eastern time zone and it knows I'm in the United States. So it pulls the holiday calendar, so it knows what holidays are, what business days are, and what weekend days are. So 19 business days is Friday, November 1st. Okay? And if you want to go in the opposite direction, day count. So this is somewhat the opposite of date plus. So let's take today and look at future business day. Well, 19, right? That's the inverse function, if you will, right? We asked for 19 business days, and now we're going in the opposite direction. From today to future and business days is 19. Okay, well, give me the holidays from today to the 1st of next year. Okay, there's 5 holidays in the United States. Give me the end of month from From today until the 1st of January 2020, we'll have 3 times an end of month: end of October, end of Novi, and end of Dies. Day count from today until the 1st of January of next year. How many Fridays? Well, 12. Okay, the number of holidays of the current year subject to the default holiday schedule. Again, I'm in the US, so that gives me 10 days, right? So we're taking today, that's first. We're adding 1 year, and we have to subtract 1 day. And what's the number of holidays? 10. This will be different for different countries and different calendars. Okay, so then I thought, how about we look at the average number of non-weekend holidays for this century for various countries. So I'm going from 2001 to 2100, and I'm asking for the business days in these countries. Then I want to display them in a table. I want to sort them, and then I want to display them in a table. And we should get this pretty soon, I hope. And one thing, I continue with the next session while this still evaluates. One thing you need to understand: holidays, weekends, and business add up to the total number of days in the range. Therefore, holidays are not considered weekend days. So a day is either a holiday, or it's a weekend day, or a business day. So the way I show this is that I'm adding the holidays, not the plus here, plus the weekend, plus the business day, and I subtract everything. Day count is just everything. Business day, weekend day, holiday, weekday, and that will come back to 0. Okay, the previous cell evaluated. So we see Germany has on average 6.3 holidays in an average of the next 100 years. So per year it's 6.3 holidays, and Japan has 16.02 holidays on average over the 100-year period. And let me show you that this comes back to 0. So keep in mind, these are separate things. A holiday can never be on a weekend. A holiday can never be on a business day. A weekend can never be, no, a business day can never be on a weekend, and so forth, right? This comes to 0. Okay, related to day count is day range. So let's look at all Sundays of the current month in the default calendar. Okay, here they are. So we can specify the day of the week here in day range. You see the last argument here is Sunday. So I start from today, I go 1 month minus 1 day, and that gives me the default calendar, the current month, and all the Sundays. So October 6, 13, 20, 27 are the Sundays for this month. Next exercise, all third Fridays of 2020, next year. And the motivation for third Fridays is that most equity derivatives exchanges have their main expirations on the third Friday of the month. Okay, so I start with the day range, with the day range from the 1st of January of next year to the last day of next year, and ask for Fridays. And I want to have the third Friday. So this is how I extract this information from the output, because this one is, of course, every Friday of next year. So when I extract this, I get these. So the third Fridays are the 17th of January, 21st of February, 20th of March, and so forth till the 18th of December of next year. I give you 2 side notes here. The above will hopefully refresh what you saw in my sessions 1 and 2 about postfix notation, in particular when we used it together with pure functions, right? When you look at this, I was trying to make a point by using left to right postfix. So then here I use gather by, and you see I always use these double slashes. That is postfix that goes left to right. We could do it otherwise. We could use prefix, but here I think I want to remind you that pure functions and postfix go very well together. Okay, yeah, the flow is left to right, and I think that feels natural for the task. Give me all Fridays in a particular day range. Gather them by the month, then show me the third column. So this is how we do that. Give me all Fridays, then gather them by the month, and then show me the third column. A second side note, I could also have used split by instead of gather by here. And I also could have used group by. And your homework is explain why split by, gather by, and group by all produce the proper split, gathering, and grouping here that we want for this question, and explain how they differ but produce the same result in this particular case. They, of course, produce different results in general, but for this one, they produce the same results. Okay, that is your homework. Okay, and another comment, the third Friday expirations of the quarter ending months are sometimes called the triple witching days. And that's because the expirations of the stock options, stock index futures, and stock index options all occur on the same day. So let me see the triple witching days of next year. Well, we just take what we had before, we partition it into 3 and take the last. So the quarter ending third Friday of the first quarter is the 20th of March next year, the second, the 19th of June, the 18th of September, the 18th of December. Those are the third Fridays that end a quarter. All right. Let me look at all the business days until year end. All right. Here they are. And we have 59. So you still have to work 59 days until the end of the year. And show me all the holidays for next year. And as I'm in the US, these are the US holidays. We just can leave out the holiday calendar specification. It takes the default. If you leave it out, it takes the default. So that's US in my case. When you run it from a different country, your default will be different. But I can also query for this information for a different country. Then I just use the holiday calendar option. And I have to point out that this is not always working correctly. For example, if I use Germany here, then we are missing the 3rd of October. Germany actually had a holiday yesterday. It was the German Unity Day. And I've just asked today on Mathematica.Stock Exchange and got confirmation it is a bug. And someone else confirmed that also for China, this list is not always complete. So when we say China here, we're getting incomplete output. I didn't verify this. I don't know the Chinese holidays. So you have to be a bit careful when you query for the holidays. Better check. All right, an extremely important function is the date difference. And if we look at the date difference here, we can just query one day and another day, and we get the difference in days. So we can again use both formats, right? The simple list, or we use these day objects, and we get 184 days or 125 days. We can ask for the difference in weeks. Okay, between these two dates, it's 235.143 weeks. And when it's negative, then you know that the order is reversed, right? We first have July of 2012, and then we have January 1 of the same year, 185 days. We have the possibility to do it in hours. We can do it in years. We can do it in months and days. And we can do it in months, days, and year. So in this case, we have 19 years, 9 months, and 3.73 days. Okay? So if you will, you can see this as an inverse relationship between date plus and days difference. So when I take a particular month and I'm adding 2 months, I store that away in days plus, and I can now use date difference and ask again for the difference in months, and I get the 2 back that I gave here as in this request for days plus. Okay, so know that we have all this wonderful functionality in terms of dates. Let's look at some visualization and harness on this. So for example, a great way to show timelines is timeline plot. Here you can see that we can use date objects. They show up as a dot. We can use intervals of date objects, and they show as a line. Very useful way to display progress of days, times, and intervals, segments of times. And please look at timeline plot in the help browser. Again, it provides a plethora of options and great examples. There's no way that I can go into all this. You have to investigate some of these things on your own. There's just way too much to show for such a short session. So for date visualization, the function datelessPlot is your workhorse. And it can take absolute time, date string, date list, date time, and time series. So it can also take numbers where you would perhaps not expect that to be a valid date that you can display. Here I'm using absolute time. And in the last one, I'm showing a number that is not an integer. Here I'm showing pi. And you can use a scaling function and reverse the scaling. So here in the first one, you see that the last one is pi, an irrational number. And with reverse, we're reversing the y-axis. You see this here. And we can use a scaling function as a mathematical function, for example, the logarithm. And you see in the y-axis here how this goes up logarithmically, 5, 10, 50, 100, 500, 1,000. And we can also evaluate things in the data itself. For example, this is pi squared over 6, and this is also zeta of 2, and we have no problem displaying that information. We see that here as the last value here, pi squared over 6. So we can use integers, we can use reals, we can use pretty much all types of one-dimensional numbers. You see the 1.644 here. All right, how about some legends? We can also display legends. We can use direct plot labels, or we can use legends. With plot labels, we label the curves, and with plot legends, we get a separate legend that is displayed next to the plot. Okay, please look at the help browser for datelessPlot. The possibilities for option and styling are absolutely endless. Again, way too much for me to show. We have time series. So let's create one. We need values, we need times, and we now can use time series to create a time series object. These things are called objects in the mathematical system. So we can then plot it with datelessPlot. This is the time series that I've just created. In parallel to that, there are also event series. Okay, here let's define a couple of values. Let's define a couple of times. Let's define the event series, and you will see that it's now an event series object. And let's plot it, and you see that we are displaying events at these dots that have a straight line down. Again, very customizable, but that's the default, right? I'm not joining them, I'm using filling. This is pretty much standard for a datelessPlot for an event series, right? And again, we can use crazy numbers. Here I'm raising e to the power of pi. Here I'm raising pi to the power of e. It's these two here for August and September. They're not too far away. I'm using pi squared over 6. So you can use pretty much whatever you want in terms of a one-dimensional value for your event series. Financial data comes back as a time series. If we are looking at Amazon from the beginning of 2015 until today, we are getting this time series. And before I show it, I want to emphasize that financial data also contains units for different types of retrieved data. So for example, when we query for open, high, low, close volume, then open, high, low, close are prices. And you see that they come back as US dollar units. Look at the hover. It says unit : US dollars. But the stock price itself, the number of shares, volume is number of shares, comes back as a unit shares. Again, look at the hover. 3.6 million shares. So it's using quantities, it's using units internally. Okay, and this data that we have as a time series here, we can now visualize in various plot types. And with this, I just want to show you 4 types of charts that are used frequently in financial trading. There's a Renko chart, a point and figure chart, a Kagi chart, and a line break chart. Okay, so this is all built in the mathematical system already. You don't need to load a separate package. You have it ready at your fingertips. Okay, next, let's look at the volume. So let's query for the volume here. And let's plot the volume. So here you see a few volume spikes. So these were days where there was particularly intense trading. We can use time series aggregate to aggregate the data. So here, for example, I'm looking for the mean of the quarter. Here's the time series. I'm now calling it NTA. I plot it. And now you see aggregated data. This is the mean for the quarter in the volume. Similar to that, there's date list stat plot. And now you're not getting points that are connected with lines. You're getting like a plateau. It's like a number that's valid for that quarter or that week, right? You get it as a plateau. And that changes only from a piecewise constant line when the data is changed, which here is at the end of the quarter. And we can also extract windows from time series. So let's again look at the full time series here from the beginning of 2015 to today. And now let's only look at 2017 and 2018. So then I say a dateless plot of a time series window, and in the window I specify start and end date. Okay, let's extract only March. Okay, so here I say 2019-3 and I say month. All right, this is Amazon for the month of March of this year. How about we extract only the end of month figures? Again, in the time series window, I can specify I want the end of month, and then I plot it, right, with automated plot markers. We can also split time series into parts and then display the parts. So let's take again the Amazon data from 2015. I split it up into 3, and now I can even get colors into it by displaying plot legends, right? We have a window 1 in blue, a window 2 in orange, and a window 3 in green. And time series are computable. Let's center a time series on the mean. Okay, now I see it that it's centered on the mean. Look at these two curves and compare, right? The blue is the time series, and we compute the mean and we subtract it. So now the center is at 0 in the orange curve. We can also double it, right? If you just want to double it, and here you see the orange curve is twice the blue curve. Not that I think it's particularly sensible, but again, I want to make the point that the data for the time series is simply computable. We can also use Brownian motion, and here we are getting a temporal data function. Note the head is temporal data. All right, so plot it. We now get 10 Wiener processes that we can display here. And these are not too far away in terms of scale, so we can display them in simple box whisker charts and distribution charts. You can also convert it to an association. That way you automatically get a legend. You'll remember from my second session that you get automatically a legend when you show it as an association. Now, this may appear more complicated for you. You have the data as a time series object, and the object is a nicely formatted container. But the format of the association is something you may sometimes also prefer, because what it does give you is that you get indices that you might prefer. For example, path 1 goes 2, right? In an association, you remember that's a key value pair. We can take something like path 1 as the key, path 2, path 3, and so forth, right? You may or may not prefer that. I sometimes prefer an association over a time series or event series object, but it's a matter of taste or the way how you write your programs. Here it's very easy to see what you're dealing with. I think that's not so easy to see immediately from the time series or event series object. And we can also use time series window on temporal data. It doesn't have to be a time series object. So let's look at the headed, where we can confirm it's temporal data. And I've created a time series window from 30 to 170. Okay, show me. And now you see that I've been able to clip off the first 30 values and clip off everything after the 170th value. right? You see that this is a subset of what you see on the left side. With time series thread, we can also combine multiple time series using a function, and I'm using mean in this case. Well, okay, it's not just mean, several others. So with this, we can look at the mean of these Wiener processes, the minimum, the maximum, the min-max, and that gives us 2 here. This is blue for the minimum, orange for the maximum, and the standard deviation, right? So you can use time series thread in order to map or combine these with functions that you apply here, the first argument, okay? Mean, min, max, and standard deviation. Okay, so that brings me at the end of today's session. There are other extremely helpful functions. I didn't talk about date value, calendar convert, histogram, time series resample. So I could do that in the next session. I also have a section that I call a nerd extension. I want to show you how precise the Gregorian calendar is by using continued fractions. So I had planned this for today, but this becomes way too much material. I wanted to leave some 10 minutes for questions. So I think I will just do this next time. You can also write me comments on the community. So let me know if you would like a little bit of a nerd extension with continued fractions in my next session, or if I should make it a separate supplemental section, then I would talk a little bit more detailed about continued fractions. Let me know in the comments, and I need to make one thing clear. I have used some material from a presentation of Nick Lariviere held at the 2018 conference last year, and I thankfully acknowledge what he contributed. So I have taken some of this material directly from his presentation in the section about data objects. Okay, so that brings me at the end of today's session. Are there any questions, Matt?
Let's see, one of our users, they have a question, the Mars time, I guess, that's the question for, our Wolfram developer. I'll ask, our internal developers, and hopefully for the next time, we could find the answer.
Oh,
I guess
Mars time?
Mars time.
You mean the planet?
Yep, planet Mars.
Yeah, this is probably something for Jeff Bryant. I am absolutely. I should probably have said this. This is for Earth. Okay, this is for Earth. Okay.
Very interesting.
What is time?
Yes,
time on planet Earth is the indefinite monodimensional physical quality that expresses blah 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 blah. Right.
So I'll find the answer, and next session, we will inform our users about the answer. So
yes, it somewhat depends on what side is facing towards the sun. This could be difficult for Neptune or Uranus, because one of these two, I forgot which one, has an axis of rotation that doesn't go up down, but it lies pretty much flat. It's in the XY plane instead of along the Z axis. It's in the XY plane. One of these two. So how time is measured on that planet and other planets, I have no idea. I plan to focus on Earth and have no intention to travel to Mars. Kind of cold, I think. Great.
Thank you, Andreas. I guess, that's a very good moment to wrap up in our session. You were watching the nice live coding session with Andreas Lauschke. He discussed timestamp data. Let me also thank our amazing team at Wolfram Research who makes the live stream possible. You can also find, the playlist of Andreas' recorded videos on Wolfram YouTube channel. You can also interact directly with Andreas through Wolfram Community. Thanks a lot for watching, and have a wonderful one.
Okay, great. Thank you.